I think it appropriate to begin this section, this application of multiple integrals in Chapter 15, by looking back again to Chapter 8, Section 1 this time, when we did arc length. And we did this in Calc 3, at least that was the case here at DeSales. And that first formula, recall this is the one that we used when we were looking for arc lengths when the functions were in the form y equaled f of x. And we'd use this one, this form, when functions were of the form x equals some function of y. And then we had this third flavor over here when we had x as some function of t and y equals some other function of t, right? And those were our three forms or flavors for what we called arc length or sector length, and that was back on page 539. If we come up to this next section where we're looking at surface area, and I pulled this equation, I believe, off of 1015, I thought it worth noting the similarity to what we were doing back in Chapter 8. And these are partial derivatives here, right? So maybe we call this one, the partial derivative of x when we have some function in terms of x and y, and this is the partial derivative with respect to y when we have some function in terms of x and y. Or as these partials are stated, this is z as some function of x and y. So let's take a look at an application problem, and this problem is number 9 from section 6, and I got a little bit of a head start, not too much here, but the surface area is lying within a cylinder, and the cylinder would have this kind of trace in the xy plane. And this is, of course, the circle, x squared plus y squared equals 1. And if we're going to set up an integral, we need to take the square root of 1 plus, and we're looking here and we're taking the partial with respect to x. We're taking this derivative with respect to x here, right? And if we do that, it seems to me that we'll just get y, and then we'll square that. And then if we take the derivative with respect to y, it seems that we'll get x. And the formula calls for us squaring that. And then we're going to have dy dx, and we have to set our limits. And that means that we have to have y as some function of x here if we're going to have dy first, if we're concerning ourselves with this interior set of limits of integration. So when we think about this, doesn't that imply that this upper portion of the circle, where the y's are positive, wouldn't we say the y's are equal to the positive square root of 1 minus x squared? And down below, when we have that portion of the circle expressed as y equals the negative square root of 1 minus x squared. So if we were doing it as a type 1, we'd be thinking about those vertical lines bounded on the top by the red down to the green, right? So our proper limit of integration on the upper end with respect to y is going to be that positive square root of 1 minus x squared, and our lower limit is going to be the negative square root of 1 minus x squared. And then our limits with respect to x, well, our x's go from negative 1 to 1. Now that looks like a pretty ugly integral, but it seems to me the technique that we just reviewed, where we turn things into polar form, might be appropriate here. Remember, that was where our conversion formulas looked like this: x squared plus y squared equals r squared. And if we need it, x equals r times the cosine of theta, and y equals the r times the sine of theta. So those are our conversion formulas, and let's dip into this just a little bit here. Remember, our dy dx is going to be replaced by r dr d theta. Our radicand, our integrand is now going to be 1 plus r squared, is going to replace our y squared plus x squared. And our outer limits of integration, when we're thinking about our polar angle, we're going to go all the way around this circle, right? So we're going to go from 0 to 2 pi. And our interior limits, when we're talking about going with respect to r, it's a circle, right? So every one of these polar distances, no matter where we are in the rotation, they're all going to be exactly 1 unit. We're going to go from 0 to 1. So that seems a whole lot better than how it started out. So now, with a little substitution, we should be in business. If we let u equal 1 plus r squared, then du would be 2r dr, but we don't need 2r dr, so let's cut both sides in half to get rid of that 2r dr. Just make it r dr by cutting both sides in half. And now we have a replacement for our r dr, right? That's going to be half a du. And let me write that half out in front of our integral sign. And so that took care of our r dr. And now under the radical sign, we'll just have a u. And let's go ahead and replace our limits of integration. If we put 0 in for r, we'll get a new lower limit of 1. And if we put 1 in, we'll get a new upper limit of 2. So working that out, we're going to get 1/2 times u to the 3/2 over 3/2, right? Square root of u is u to the 1/2. If we integrate that, we add 1 to a half and divide by that number. And upper limit is 2, lower limit is 1. If we flip that fraction in the denominator, half of 2/3 is going to be 1/3. And then we've got u to the 3/2 with an upper limit of 2 and a lower limit of 1. So it seems to me that we have 1/3. If we put 2 in and cube it, we get 8, and 8 to the 1/2 is the square root of 8. And if we put 1 in, 1 to any power is 1. And that's the evaluation of our interior, right? That was this, we've just worked out this first part. So now we've got to carry that answer forward and do a little bit of part 2, which is pretty simple now. 0 to 2 pi. We've got this big constant here, 1/3 radical 8 minus 1 d theta. So when we integrate that, we'll get 1/3 radical 8 minus 1 times theta with an upper limit of 2 pi and a lower limit of 0. And if we put the upper limit in, we get 2 pi times 1/3 is 2/3 pi. 2 pi over 3 times the square root of 8 minus 1. If we put the lower limit in, we get 0. And there is our answer. That's the number of square units for this area. I got a little bit of a head start here on number 3. We're talking about that part of the plane that lies in the first octant. Well, the trace line in the xy plane, that is where z is 0, would be the line 3x plus 2y equals 6. And so we're bounded by the xy plane, as well as the xz plane, which would be, the trace line would be this line right here, right? This line called y equals 0. That's the x-axis. And the other boundary, oops, let's undo that little movement there. And this boundary here would be the YZ plane, and this is the one where the x's are 0, right? So you can imagine this plane coming out straight at you along the z-axis that's coming out right at us, and then we have this plane down here where the y's are 0. It's called the xz plane coming out at us, and then the trace line in the xy plane is the green line that I've drawn. To do this as a type 1, we might want to restate this, right? So let's take and write this guy as, you can see the slope is negative 3/2, and the y-intercept is 3. So that might be a better way of rendering this. So that would be our upper limit and our lower limit when we do our setup. So let's go and pay attention to our setup now. Remember what that looks like. We've got that radicand, or integrand, excuse me, that has that big radical sign. And under the radical sign, we have to think about this as z equals 6 minus 3x minus 2y. And so if we take and find, and let me just go back and grab that formula so we're have it here as a handy little reference. That's what we're using. So under this guy we're going to have 1 plus, and then we'll take that derivative with respect to x, and it seems to me that we'll get negative 3, because this will be a constant and this will be a constant, so these will go to 0, and we'll get a negative 3 for the derivative with respect to x, and then the derivative with respect to y will get a negative 2. And our upper limit will be the negative 3/2 x plus 2. And the lower limit will be 0. And then paying attention to our x's, our smallest x is 0 and our largest x is 2. Now, working on this, we have the square root of 14 here. Upper limit negative 3/2 x plus 2. So this is going to be radical 14 y with our upper limit negative 3/2 x plus 2 and our lower limit 0. So we'll have radical 14 times negative 3/2 x plus 2. And of course when we put 0 in we'll get 0. And now we've got to do part 2, right? I wrote radical 13. I'm not sure why. Let's clean that up a little bit here, right? Oops, I really cleaned it up too much. Let's straighten this up here. This is radical 14y. So this is going to be, we said, radical 14 times negative 3/2 x plus 2. And then we're going to come back at it and integrate again, right, with respect to x. So maybe I kick that radical 14 out front. And I'll have negative 3 over 4 x squared plus 2x with an upper limit of 2 and a lower limit of 0. And so I'll have radical 14. If I put the 2 in, I'll get 4. And 4 times a negative 3/4 will be a negative 3. And we'll have a negative 3 plus 2 times 2 is 4. If we put the lower limit in of 0, of course we'll get zeros there, so we won't even write that down. So our answer very nicely is going to be radical 14. I get all the way to the end here and I notice that I have made an error. I'm not quite sure how that happened, but wasn't watching. That's how it happened. That was supposed to be a negative 3/2 x plus 3 from our equation over here at the right for our boundary. So I'm going to fix it because it is going to change our answer, right? And And so that's supposed to be plus a 3. Let's fix that up again here. And fix that up again here. And fix that up again here. So that's supposed to be a plus 3. And that's supposed to be a plus 3. And that's going to be a plus a 3x, right? So now we'll get negative 3 from the first term and 6 here. So thankfully this repair wasn't too bad. And so we'll end up with a 3 radical 14s. I was just glancing at my answer there, and I saw that I had forgotten to write plus 3. I had written plus 2, so we fixed all those up, right? Maybe you saw it. I hope you saw it right along and said, what's he doing? All right, so we caught it right at the end. So it made those changes. This is number 1 from page 1016. And maybe I should have started with this one, but I started with number 9 because it related to a previous section, and then certainly example problem number 9 relates to an earlier section, and well, one, we'll just take a look at it. These lines, the red lines, are the lines y equals 1 and y equals 4. And these dimensions are over here, 1 to 4, the rectangle, and then the green lines, the vertical lines, are the lines x equals 0 and x equals 5. And they correspond to what's given in the problem. And then we're going to take and write the derivative now, the integral, the double integral. We'll hold off on the limits for the moment. We'll write the square root of, for our integrand, and it'll start with a 1. And then the integral of z with respect to x, it seems to me that's just going to be 3, because the other two terms will drop away because they're all constant, right? So we'll have plus a 3 squared. That's our dz dx quantity squared. And then the other derivative here is supposed to be dz dy. So that'll be 0, that'll be 0, that'll be a 4. And we're supposed to square that derivative, right? And then we'll do the order dy dx. And our limits for y are from 1 to 4. And our limits for x are from 0 to 5. So this problem rather straightforward here, right? Because this works out to 16 plus 9 is 25. That's the square root of 26. Not as nice as it could be, but that's what it is. And we're going to get a y when we integrate with an upper limit of 4 and a lower limit of 1. So we're going to have 4 radical 26s minus 1 radical 26 is going to be 3 radical 26. And then we're going to come at it one more time, 0 to 5, and we're going to integrate with respect to x. So it seems to me that that will be 3 radical 26 x with an upper limit of 5 and a lower limit of 0, and we'll get 3 times 5, or 15 radical 26 minus 0, and our answer, 15 radical 26s square units, right? So that would be our answer to number 1. And we'll pick up on this the next time we meet. Thank you.